Okay, good afternoon, everybody. I see it just hit 1 o'clock on my screen, so we're going to go ahead and get started. I'm sure some more folks are going to be joining us. Want to welcome you all to today's webinar. We're going to be talking about using infrared thermography for condition monitoring. Just a little bit of housekeeping before we get started. For those of you that are new to UE Systems, my name is Maureen Gribble. We do these webinars once a month, sometimes more than that, and we, even though our company focuses on ultrasound and providing inspection equipment for folks to do on anything from leak surveys to electrical inspections, lubrication, mechanical inspections, and all that good stuff, we definitely understand that we fit into a bigger picture of reliability and asset health, asset management, whatever you want to call it. So we like to find folks who can talk to those other pieces of the puzzle, so that we're all just very well rounded in our education and understanding that there are plenty of different predictive technologies out there, and we all complement one another. So today is not about us. It's not about ultrasound. Instead, we're going to happily be talking about infrared, which so many of you are very interested in. So we've got a great group, and we're really excited to have you all with us today. So the way this works, we are live, so we, even though we can't see one another and we're all spread out throughout the globe, we do want to try and make this as interactive as we possibly can. So please feel free to ask questions throughout the webinar. I'll be keeping an eye on those, and we'll get as many of those asked to our presenters as we can. Certainly, as time permits, we might have to hold off and get some of those questions answered offline, but we'll do our best to make sure everybody's getting the information that they need. A big question that always gets asked, yes, we are recording this, and we will put this up on our website. I'll also be providing the recording to Matt and Gary so they can have it on their website as well. So definitely, if you have to hop off early, if you've got colleagues who couldn't make it, whatever the case may be, we'll have that recording available for you. And if you want the specific link for what's going to be on our website, just put that put a little question over to me, and I'll get you my email address so you can shoot me a note and we can get that over to you. So keep that in mind. And also, again, since this is live, we always have the possibility of some errors and technical things happening. So just bear with us if we lose audio or internet gets slow or something. Just bear with us, and we'll get things fixed as quickly as we can. But I do find that it's nice being able to host these live, and with that we take the risk with the reward. So with that, I will stop yammering on, and I will turn the screen over to Matt and Gary and let them take it away.
Thank you, Maureen. Good afternoon from our Boston Regional Training Center. How are you doing?
Well, I'm good.
Gary Orlove.
I was going to answer for everybody else. I think we're all doing great.
Well, joining me is Gary Orlove, and we'll just do some introductions here in a moment, but we're glad to be here. UE Systems, I've known you guys for 15 years now. In fact, I first got started in the industry going around doing seminars with Mark Goodman and others, and Doug. And so it's good to come sort of full circle here and get on with you guys this afternoon to talk about infrared for condition monitoring. Joining me is Gary Orlove, who's our Global Curriculum Director and an ASNT NDT Level 3. Hey, Gary.
Hey, how's it going, Matt? Hey, Maureen. Nice to be here.
Gary will be on here. We're going to just go through these. If you have questions, as Maureen said, feel free to send those in, and we will get those at the end of the presentation. But to sort of just give you an overview of where we're headed here today. Wanted to introduce the Infrared Training Center to those of you that are on board with us this afternoon. Many of you might be familiar with ITC, others perhaps not, and what we offer for services in the industry as really the leading thermography certification support and service company out there. What we'll get into here in a bit is Gary and I are going to discuss thermal imaging, and we're really where it's applied in predictive maintenance, reliability maintenance, whatever you want to call it. And I want to tie it back into why training and certification is really ultimately necessary for thermographers. And what we'll do is we'll mix in some of the training elements that we talk about in our courses, specifically our level 1 classes, and how those lesson items, how they relate to using thermal imaging for electrical and mechanical applications. And so we'll sort of all tie that together. And then at the end here, we'll take questions as well. As Maureen might have mentioned, we're coming to you from our Boston Regional Training Center. This is the classroom just across the hallway from our production studio, where we host a number of classes and, again, study not just the basics of infrared in terms of the equipment operation, but also how infrared is utilized, sort of the theoretical side, the stuff that you have to know as a thermographer ultimately to be successful with the technology. The science really plays an important role in understanding what it is we're seeing thermally. And it reminds me sort of, you know, where we've been and where we are today. Cameras not too long ago were very expensive, very large, very cumbersome. Some would say difficult to use, and we've really come a long way. Gary, I think in your experience.
Yeah, that camera that you see on the left there is very similar to the one I started with. Actually, we had no color, no video output. All the documentation was taken off the screen, which was a Tektronix oscilloscope screen by a Polaroid camera. And it didn't run on batteries.
And to today, where you can literally put an infrared camera in your pocket. And with that change in the size of the equipment, the price has also come down considerably as well. Cameras are very inexpensive, comparatively speaking, to what they used to be many years ago. But the point here of this slide is what hasn't changed is the physics behind how the technology works. That's ultimately where we're going here. And so understanding infrared science, just as important today as it was back 10, 15, 20, 40 years ago, what have you. That's because we're dealing with an entirely different spectrum of energy that's out there. We're obviously very familiar with visible light. It's what we see with our eyes. We grow up looking at the world visually, and with that we see the colors that are associated with the visible light spectrum. Infrared, a whole different wavelength of energy. Things look very different. Gone is the color. We don't see color with this technology. We see the heat that's radiated by all objects. That heat radiated is what the cameras see. The detectors actually pick that energy up and interpret that and convert that signal into a temperature value. So understanding the physics behind radiation science is really critical to really understanding this technology and what it is you're seeing, regardless of the price of the camera, whether it's an iPhone attachment or perhaps something that's, high-end, commercially available handheld thermal imaging system that could be tens of thousands of dollars. Understanding the physics is really important.
And one of the things you just mentioned, Matt, that IR really doesn't have a color per se. And it's true. The basic IR signal is just a black and white signal. And what you see here with the handprint is actually a colorization by a computer system.
So just last week, I was down in Fairfax, Virginia for a level 1 thermography training course. And we had about 20 people in the class. And what was interesting about this is, well, of course, we have hands-on exercises to reinforce the things that we discuss throughout the course of the week. And during one of these hands-on exercises, we were out actually behind the hotel, and the students ended up locating in some pretty challenging conditions one of the hottest thermal anomalies I think I've ever seen in my 15 years of teaching. It was a disconnect up on a power pole that was out behind the hotel. This was the third day in the afternoon, pretty, bright sunny day, so we had a decent amount of solar loading, considerable wind, and yet this still showed up. I'm going to bring this back in, I think, a little bit later on here, but I want you to see that those temperatures there. That's not a typo on the slide. At a minimum, this thing was hundreds of degrees warmer than what it should have been. In fact, we're seeing a max temperature here in the lower right side of over 500 degrees Fahrenheit. That's 260 Celsius. Now, there's some issues that were going on here in terms of we were at a distance, there's emissivity considerations, there was convective cooling. There's a lot of things that's telling me that this was probably a lot even hotter than what it appears to be right here. But the point here is with the exercise that they found this, discovered it, actually reported it, and the power company came and addressed it. But that equipment operation, the hands-on equipment operation, is one of the things that we focus on in the class, and so this was a great find. Really kudos to the course for the people that had attended. But the tie-in here is knowing how to operate your equipment is critical. It's why we have the exercises in our classes. It's why we focus on things like focus, like image adjustment, all the basics of imaging. Optical focus, very important. In fact, without good optical focus, very difficult to identify what it is you're looking at. So during training classes, we spend a lot of time working on the equipment operation. You might not realize that focus doesn't just affect your ability to see the target, it also affects temperature measurements as well. It's an image of a fuse cutout that we have here in our lab in Nashua, New Hampshire. We use this as one of the targets during our infrared training classes, and I use it as a way to demonstrate really the importance of focus on adjustment of the image. I don't know if that's going to load here. I don't think it's loading. Unfortunately, I don't think it's coming up, but as Maureen said, we do have technical issues sometimes. But the important point here is that if you're out of focus, your temperatures are out of focus. They will not register as clear as they should. And so proper focus is essential for getting good images with infrared. Having the right equipment with the right temperature range, also really important. Different thermal imaging systems come equipped with different temperature ranges in which they operate. So knowing what your application is really important as well. If you're just doing basic building inspections, one temperature range is likely sufficient. But if you're working with more high temperature applications, looking at refractories or perhaps furnace applications, you're going to require a much higher temperature range in which to operate. This is just one example here. Temperatures approaching probably Gary, what do you think? Maybe giving off visible light almost?
Certainly some of that right at the top there, or what's inside.
So camera selection really important for understanding, what the capabilities are. Image adjustment in terms of the scale, how we adjust what's called the span or the level, very important to know. In an outdoor substation situation like this, where much of the field of view is occupied by the sky, when you use these cameras, if you don't know how to properly adjust the scale, you're likely going to miss critical problems. And that's another thing that we emphasize in our training classes is the right tuning or thermal tuning, which is span and level adjustment. The span and level are part of the overall range of the camera. So if you have multiple ranges, being in the right range is important initially, but then adjusting that scale becomes just as critical. Here with proper span and level adjustment, we can now see a hot connection here in this outdoor substation, something that was not really detectable here a moment ago. And then I mentioned resolution. This is back to that example from our class last week in Fairfax, Virginia. Resolution. Can we actually see the target? And are we close enough to get an accurate temperature measurement? Very important. Different cameras come equipped with different resolutions, different resolution capabilities. And so understanding the resolution or what your camera can resolve for details at a given distance, very important as well if you're using infrared in condition monitoring. To understand resolution, you first need to understand that the image is built from pixels. The detectors inside the camera, that's what the lens focuses that energy on. Those infrared sensors are made up of thousands and thousands of these detector elements. And depending on the size of what's called the focal plane array, dictates how many detectors you may have. On the lower end, you might have an 80 by 60 focal plane array. Perhaps on the higher end, a 640 by 480. And that's how many pixels there are across both the horizontal and the vertical in the image. More detectors essentially means capturing more thermal detail. But that's just one part of the resolution equation. It also brings into consideration the lens. But to think about it this way, resolution is essentially how many detectors do I have on the target? If I have a house, let's say, and I'm doing an inspection, but let's say that house is down the street, too far away, I'm not going to get very many pixels or detectors on that target. We won't be resolving much. You might just see a hot little dot there in the distance. Not really good resolution. But to get better resolution, I either have to get closer or use some type of a different lens to put more detectors on the target. And that in essence is resolution. How many detectors do we have on that target to be able to resolve details correctly? Back to this fuse cutout here in our Boston Regional Training Center. We use it as a target to actually do a practice on resolution and the effects of distance to target. On the left was an image taken at about 5 feet away. We can see there a temperature of about 178 degrees, and that's with the spot meter filled completely by the target. On the right, however, is that same target, but at a distance of 32 feet. If you notice there, we see a pretty significant temperature change. That's because the resolution has been affected by this distance. Now, the resolution is a fixed value, but that they're further away now, we're actually getting less detail. And with that, not good resolution on that temperature. Emissivity, another thing we have to look at, the efficiency with which an object can radiate thermal energy. This is a copper bus bar lab that we have in our training labs. We can see here very clearly an apparent temperature difference of only a couple of degrees that show up without any emissivity adjustment. One of the things we emphasize is the impact that emissivity has on thermographers, especially in the realm of condition monitoring, and specifically here, electrical applications. If you're looking at lower emissivity targets, which are typically your unpainted metals, metals are things that do not radiate heat efficiently, the temperatures you're seeing are less like what the target really is and more like the surrounding, because we're not picking up that energy coming off of that target very well at all. Here we see what appears to be only a 2-degree difference on these shiny copper bus bar surfaces, when in reality the temperature differences is quite significant, on the order of about 75 degrees or so. And we can see that now because of the electrical tape allows us to better resolve the actual temperature of the surface. Now in this case here, this is a mock-up that we can safely touch, but if you're in an industrial situation where you have energized equipment, this is not something that you could easily do or safely do. And so that presents a unique challenge for thermographers that you have to really understand. And as we see that temperature difference, it also happens that emissivity affects our delta T's. On these 3-phase fuse here, we've got 3 phases here. On the C-phase connection, we notice on the fuse body a temperature of about 125 degrees Fahrenheit. That's on the lower side there. Up top on the A phase, a temperature of about 91 degrees. Yet if you look at the fuse caps, you can see that your temperature differences are also affected by this emissivity issue, something that thermographers doing industrial maintenance inspections really need to understand. And going hand in hand with emissivity is reflectivity, and thermal reflections are something that as thermographers we're dealing with all the time. You might be looking at energized bus bar and see a very unique thermal pattern, such as this. When in fact that temperature that we see there has nothing to do with the actual temperature of that surface, and looks quite interestingly, Gary, like my left shoulder. I don't know.
That's right. Well, some people actually use this to try and find ghosts and apparitions, and often when they think they're seeing an apparition or a ghost, it's really a reflection of their own body heat.
And that really a great point that you lead to there, Gary, is if you see something that appears to be hot and you're not sure if it is, move. Good thermographers are always on the move, changing their position. And if the hot spot moves, what you're seeing is likely a reflection. And that's sort of illustrated here on the left as we're looking at this connection here, very perpendicular. On the right, we've now moved and the reflection moves. And that's one way of identifying false negatives, or I guess false positives, I should say, in this situation. So it's not just radiation science that we discuss. We also get into things like convection, conduction, heat capacitance. Because as thermographers, you have to know that oftentimes what you're seeing is really what we call indirect heating. It's actually the surface temperature. It's not the fault. It's not the problem. On this load tap changer here, we see a slightly elevated temperature of about 116 degrees Fahrenheit. It's on the left side of the image. Now that's a pretty accurate temperature measurement of that surface. It's a painted gray metal surface, very typical of what you might see in a substation. But that's just the surface temperature. It has nothing to do with really what's happening inside. And that's when we talk about these other modes of heat transfer. Because when you look inside, we now see that the oil has in fact coked up. And I don't know about you, Gary, but I don't think that happens at 116 degrees.
No, it does absolutely not. And that's something also always to remember too, is that infrared cameras are looking at the surface radiation or heat pattern of things. They're not, by and large, looking into buildings, shall we say, as you may have seen on some Hollywood movies or television broadcasts.
Gary, besides being our global curriculum director, heads up our information conference, which we have about every couple of years or so. Next one's coming up in 2018. It'll be in the fall. This event showcases really the best practices of thermography from professionals like yourselves from around the world. And a couple of years ago, actually back in 2015, Daryl Androli of Missouri Energy Services came and presented in Nashville. And this was a very interesting presentation, kind of an eye-opener, which really, I think, I guess, put to bed the myth that you can see through electrical panels and not have to remove covers. Daryl was inspecting a lot of 480, I think, what is 480 volt bucket
Right.
motor control center panels. On the left was with the door closed, a max temperature of 91.6 degrees on the outside. Inside, with that cover open, it was over 873 degrees. And as Daryl says in his presentation, you could not see that with the door closed. And so we need this direct line of sight. Now, of course, with access comes safety issues, which we don't really get into. We do mention it and talk about 70E in our classes, but you need that direct line of sight in order to see something. I get the question a lot, you know, if it's bad enough, it'll show up. It really won't. And so that's something that you have to be concerned with as an industrial thermographer.
Yes, and going back to that particular slide, I mean, the modern way to do this, to be able to see and stay safe, is to install an infrared window in that piece of equipment so you can inspect it while it's closed and look right into the equipment with your infrared camera.
It's a simple little lab that we do in our level 1 training courses, our Indirect Heating Lab. It's basically a painted gray metal box with an incandescent light bulb on the inside. Very typically what we'll see on the outside, students that are doing this exercise, are temperatures in about the 110 to 120 degree Fahrenheit range. And when they open up that top and they look inside, they actually have to go to the next range on their camera, if they even have it, because temperatures are approaching 400 degrees in some instances, depending on what we've got this plugged into. Just really demonstrating, I think, the dramatic difference that there can be from inside to outside, whether, you know, it's not a light bulb in a box, it could be bus bar and bus duct, something inside a load tap changer, whatever. It really, I think, demonstrates that very, very, very nicely. And so in a situation like this, you then learn that if you're seeing this with, you know, oil-filled circuit breakers in an outdoor substation, and what appears to be a very subtle temperature difference between two of these OCBs, it's really much more significant. And in fact, if it's this case, you could almost say it's probably game over at this point. Because of that, how much heating there is on the inside to generate even that little bit of a signature on the outside, Gary.
Right. I mean, that heat generated at the contacts has to travel through all the oil, then through the casing to display on the outside.
But indirect heating, it's not just electrical equipment with motors. We say that, generally speaking, a rule of thumb, there's about a 20 to 25 degrees Celsius temperature difference from what you're seeing on the outside of the motor casing to what's happening inside that motor. And so if you actually pick up localized heating like we might see here, tack on about 36 Fahrenheit, and you get a rough ballpark of what the heating might be inside that motor to see that if it's exceeded the threshold that's on the nameplate data. That's something, obviously, of a motor, you know, very expensive piece of equipment. Infrared can help us diagnose these problems. We can detect these things and try to prevent, you know, permanent damage to this device. And with motors, and generally speaking, just looking at the overall temperatures, if I've got two motors and they're both under the same load, same class motor, doing the same work, and they're in the same environment, they should all be about the same temperature. And that's, again, with thermography, we can get a read on that. Now, other technologies will better pinpoint exactly what's happening with the motor. Ultrasound is one of them, obviously. Vibration is another. They also have electric motor testing, but infrared just one of a number of tools that you're going to want to use in electrical maintenance applications, specifically with mechanical equipment. Here we have a temperature, elevated temperature on a motor bearing. Would be a great thing to listen to with ultrasound, but with infrared, we can now see an elevated temperature, a few degrees above the motor casing, really nothing to be concerned about. But if it's significantly warmer than that outer temperature there of that housing, that's something you might want to look at a little more closely. With steam traps, obviously with ultrasound we can listen to steam traps, but with infrared we can find temperature differences. And that's what we want to look for, a temperature difference from the inlet to the outlet side. With this type of thermography, by the way, I don't want to sort of steal a term from another area of the industry, but it is kind of active thermography in the sense that you want to be actively looking at this as this is happening, right? As the trap is cycling. It's not just taking a still photo and walking away. You want to see this cycling, right, Gary?
That's right. Steam systems can be rather difficult to diagnose because the thermodynamics of steam in the entire system can play tricks on you. Actually, in these particular images, that clamp that you see on there is actually a clamp with a ultrasound detector on it, because ultrasound actually, in the end, does a better job of diagnosing these. But it generally requires a touching, and so you can at least get a rough idea of the steam traps condition with the infrared. But as I said, it can be a difficult thing to do because you could have condensate pressure backed up in the condensate line, or other traps blowing through, raising that pressure, therefore raising the temperature there too. So a small temperature difference versus a large temperature difference doesn't always really pan out. And some of the things that to do for looking at steam traps is to check the inlet temperature. If it's significantly below that steam temperature, then that indicates that a trap that has failed in the closed position. Or it might be also that the trap is undersized and not able to, and condensate is backing up on the inlet side because it just can't remove the condensate. A pressure differential across a trap will produce a temperature differential as well. But a properly operating trap will intermittently charge condensate very often. So if you look at it with the infrared camera and you look in that exit and you see a pulse of heat every so often, that means you have a trap cycling there, because you have a slight temperature increase because the flash steam, condensate flashes the steam at the outlet and raises that pressure briefly. But the ultrasound is what really helps diagnose this properly, and it's probably the preferred tool.
And you mentioned stuff about valves earlier too, Gary. Was that right? Did I hear we were talking before this, valve operations?
Well,
infrared's certainly one thing we can utilize here. Here we've got bypassing on a closed valve. It's actually in the closed position, and we can see thermally, not because we're seeing through the tank, but we're seeing that basically cooler fluid is pulling or conducting more heat into that tank, and now we see the cool signature there. But with ultrasound applications too?
Oh, absolutely. That's one of the big reasons that you use ultrasound for these kind of things, because each of these valve leakages, etc., produces a unique sound signature that ultrasound can very quickly and easily pick up.
Infrared, great with tank levels. It's one of the reasons why we talk about heat capacitance in our level 1 classes, the difference in heat capacitance between different types of materials, solids, liquids, or gases. We've got sludge in this situation here. We've got a liquid, which is crude oil, and then, of course, sort of an air gap at the top. And what happens here is that throughout the day, as the temperature changes, as the sun hits that tank, different materials will change temperature at different rates. That's the essence of heat capacitance. And things with a higher heat capacitance take longer to warm up because they require more energy to change temperature than things with a lower heat capacitance. So liquid inside a tank, very slow to change temperature, whereas that gas or that air gap changes temperature more readily. And we can see here, make out a very nice level inside that tank. There's also quite a bit of sludge as well. This was an interesting situation. Infrared is really not a technology to use for things like air leaks because we can't see air. We can't image air into air. That air has to be hitting a surface and changing its temperature. Having said that, there are times we will catch something like this, which is being caused by the bypass of air because of a negative pressure in this situation. I believe this was on a return steam side of a turbine at a facility. And that actual nut you see there that's cooling is because ambient air is being drawn in because of the loose bolt in this situation. And that pressure imbalance, as it was explained to me by Ron Lucier, could have been had a pretty high price tag on it potentially, I think, because of what was happening.
Yes, I don't recall exactly what the numbers were, but that bolt is cooled because of the adiabatic cooling of the pressure difference of the air there. It's a very dramatic thermal image. Again, this is something else that ultrasound can definitely locate and identify.
Kind of back to the electrical side for a second, oil tubes, oil fins in a transformer. We can see if there's a blockage, a low oil level, perhaps a leveling issue with that. So what you want to see is on the right, a nice thermal gradient, hot to cold, as that oil convectively cycles through those tubes. On the left, perhaps some type of blockage that's causing or preventing the oil from sort of cycling properly. With bearings, I know you can listen to bearings with ultrasound, but we can also see it with infrared. And if you've got multiple bearings, hundreds, thousands of these perhaps to look at, thermography can be used to identify problems with bearings, but I know they do listen to these with ultrasound as well.
That's right. Well, on these long conveyor belts, infrared can be extremely useful. I was out at a facility in Australia where they had a mile or two of conveyors, and you could just drive along next to the conveyor belt in operation using the infrared camera and help spot the bearings that had issues.
We talk about belts, drive pulleys, belts, shivs, whatever you might have here, should be at or near ambient temperature. Any change in temperature could be several causes. Now, here's another situation where thermal imaging might not necessarily pinpoint exactly the problem that you're having. It could be a tensioning issue, could be an alignment issue, could be a mismatched set of belts, which is certainly going to cause heating to show up there. But at least we're tipped off to the fact that something is happening, and we're going to want to investigate that more closely. In terms of electrical connections, there's really two types of electrical problems that you're going to run into with thermal imaging. It's either a high resistance contact problem, that's a connection problem, where it's hot at the point of failure, and then the heat, as it conducts away, gets cooler and cooler, that thermal signature. The other is an overload or an imbalance, where the entire phase, let's say, is at an elevated temperature, and that could be simply just because it's carrying more load for whatever reason. Here on this transformer connection, classic connection problem, we see temperatures here, but honestly, we don't need to have a temperature to know we've got a problem in this situation. With a dry transformer, the classic overload, the coil there on B phase at an elevated temperature, simply because it's carrying more load. But there's several things here that you want to look at, not just the temperature of the coils on the lower image, it's also the connections at the bottom of the transformer. And this is again where access can be an issue, because we have to take the metal cover off to get that direct line of sight. And if we're doing that, we need to be a qualified operator. And I think just to tie it all together here, I don't know if you want to pitch in, Gary, chime in on this. Really the value of infrared is not just finding the problem. As we think about thermography, as thermographers, we're in the sort of the world where we have sort of this very acute sort of vision of what we're doing. And that's trying to find, let's say, an electrical problem or an overload, and not really thinking of the bigger picture. That is, what happens if this were to fail? And part of this is obviously planning for better maintenance. Following up is a critical thing to consider too, in that you might find or locate a high resistance connection problem like we see here on the left, and you might report that and generate a work order. But then how do you verify, or do you have plans to verify that the repair actually was successful? On the right, we have that verification. Programs are getting, I think, more savvy to the fact that this sort of follow-up inspection is really where they're going to realize a lot of benefits with infrared. Is not just finding it, but also following up, because sometimes the repair simply doesn't work.
Yes, that's right. Simply the repair doesn't work, or the repair was not appropriate to what the root cause of the problem really was. And so by looking at the follow-up inspection and still noting if there is still a problem there, that just leads you to dig in a little deeper and find out really what's going on here. And just tightening a screw may not have been the thing to do.
I mean, not everything's fixed by a quarter turn, Gary.
That's right.
I think every electrician I've ever met has always said, just give it a quarter turn. And that quarter turn might be one quarter turn too many, because you can warp a connection. Certainly the environment has a say in how things, the health of equipment, whether you're at a pharmaceutical facility, pharmaceutical plant, or you're working in a pulp and paper plant, which are probably on the spectrum, the two furthest things in terms of how clean the facility might be and whatnot. The conditions, the environmental conditions obviously play a role in this as well. But what this really gets sort of into is, we get the question, probably the most common question is, well, how hot is too hot? I guess I don't have the specific history on this particular fault. I do know, however, it's a critical problem, even though the temperature we're seeing there doesn't appear to be that serious.
Yeah, that's right. I mean, you have to look at what kind of equipment it is, and if that equipment fails, is it a big safety hazard or a big operational hazard, such as taking down an entire plant? So, sometimes the lighting panel, which we may not think of as being very important, could be extremely important. For instance, if that lighting panel happens to serve an operating room in a hospital and the lights go out, that's pretty important to the patient.
Yeah, absolutely, absolutely. And I get that question a lot in class. People will come to class and ask, well, I need to measure temperature. I have to know how hot something is. And what I try to instill in our students is yes, that temperature is important, but it's also not the only data point that we need to consider. We have to really ask more than how hot is it to get to the root of the issue. And that's what I'm getting at the bigger picture, is that it's not just about temperature. It's not just about the probability of failure. It's also about what are the consequences of failure should this obviously go to failure in this case. That it's 104 degrees, I think, 105 degrees. Honestly, I don't really care. It's a transformer. It's a center phase. It's a critical component. It's probably powering a facility in some capacity.
Right.
If this thing were to go down, what is that outage per minute, per hour, per day? Mm-hmm. That temperature is really a secondary consideration. The fact that we have a difference here, a much, much bigger concern. And so when we talk about in our level 1 training classes, and we talk about temperature-based prioritization, we sort of take it with a grain of salt, in that the thermographer needs to understand that knowing exactly how hot it is isn't the only consideration.
That's right.
These charts are all over the place. This one's from NITA. Some companies will make their own charts. We just want to sort of leave you with this, and that is if you're using infrared already, consider more than just the temperature of the fault when it comes to prioritizing something. Because what we find here at the end of the day, even after we've had training, is that temperature readings are not always reliable for a variety of reasons, whether it's emissivity, whether it's indirect heating, like we showed you earlier in this presentation, whether it's convective forces, such as winds that are cooling off objects, resolution-related issues, and the list goes on and on and on. Things that these temperature tables don't address. NITA just gives us these numbers, but doesn't say what the limitations are to actually getting those numbers might be. And while these numbers might be, let's say, based on a fully loaded circuit, they don't take into consideration all the things that we just talked about. And that's why training is essential, because as a thermographer, you have to be thinking in multiple dimensions all the time and not just accepting what the camera is telling you at face value. And it's not the fault of the product. It's not the infrared camera. It's physics that is lying to you. And that's why thermographers need to be trained and educated properly. You think so, Gary?
Oh, absolutely. I mean, the most important tool in any condition monitoring application and technology really is the person behind it and how they're thinking through a problem and for diagnosis. You just can't rely on a piece of equipment saying green or red. It's green's okay, red's not okay. It's not black and white like that.
So if you want to learn more, the Infrared Training Center obviously can be that resource for you. We provide knowledge to thermographers from around the world at multiple levels of training. We're very active on social media. If you want more on Twitter, Facebook, YouTube, even Instagram or LinkedIn, check us out, give us a follow, give us a like, where we share things like live webinars and tutorials that we run on a very frequent sort of basis. We have valuable tips, free white papers, special offers, you name it. If you liked what you saw this afternoon and you want to learn more, go to any of these channels here where you can join us and actually join in the conversation. I had shared the Fairfax find up there, and it was one of the more popular posts we've had in a while. Of course, there's our website, infraredtraining.com, infraredtraining.com. You can email me as well or send a general email if you're interested perhaps in training, both at our public courses or on site. Hope you consider that as well. You could check that out. But at this time, Maureen, I think we're going to toss it back to you to see if we had any questions that might have come in during the broadcast.
Yes, awesome. Well, thank you guys so much. Great information, and loved all the ultrasound shout outs. I know I said it wasn't going to be about us, but let's face it, we always like to be brought back into the fold, so we appreciate that. So we did have some questions coming through, and feel free if you guys are still on and have some questions, send those in. We got some time here. So one of them that came in early on was, can we interpret temperature below atmospheric temperature? Which I'm not totally sure. I think that's what they meant to say. Yeah.
So can we see things that are below ambient?
Oh, absolutely. Yes. The infrared cameras today can not only look at very high temperature objects, but we can look at very low temperature objects too. Some cameras go as much as 40 degrees Celsius below zero for their temperature measurement ranges. So yes, absolutely. And sometimes what's coldest is an indication of a problem rather than what's hottest. All depends on the system that you're looking at.
Interesting. Okay. And someone was asking how exactly the IR windows work.
Well, infrared windows are just made of a very special material that will transmit the infrared, such as calcium fluoride, which is a very typical window material, or some kind of special kind of plastics are also used on these materials. Unfortunately, ordinary window glass or quartz will really not transmit infrared at all. So that's why we have to go to some of these special materials.
And with infrared windows, you have to know the transmission rate of the window, because it is what we call an attenuating medium. Basically, 99.9% of what we look at is thermally opaque, can't see through it. But a few things like infrared windows which are made of these materials, but they're not 100% transmissive. And so you have to know what that transmission value is. And it tends to be a lot lower than you might realize. And if they've already been installed, it can present a challenge. If you haven't installed windows yet, it's probably in your best interest to test those windows prior to installing them in order to know what that transmission rate is, so you can get a more accurate reading behind it.
All right. And when you were talking about motors, someone had asked how it was that you know to tack on the 36 degree to estimate the internal temperature of a motor. They were just wondering where that information came from.
That came from me, and I looked at Gary here because we looked at each other. That's just something that's been one of those sort of constants forever in the industry. It was taught to me by some of the best thermographers in the world when I first started off. It's a question, I guess, chicken and the egg. Where did that come from? Where did they get that information from? But that's sort of always been my understanding as the rule of thumb. But
yeah, I remember one of our instructors had something on that. I can't remember what the actual number was because he had quite a bit of experience for those motors.
I know in our classes we say 22 Celsius specifically, so I've always said 20 to 25, somewhere in there. We have to check, Maureen. We'd have to check to see if there is a source for that. But that's sort of been, as I've understood it, and these are AS&T, NDT level 3s that I've gotten this information from. So I would defer to those, but I don't have a specific source on it.
Okay, no problem. Okay, so in regards to belts, someone was asking, belts that are slipping, will they cause more heat or less heat?
With belt slippage, you're going to see the belt heating up. That's certainly one thing that's going to happen. And around the pulley or the shiv or whatever, it's also going to heat that up as well. So with loose belts, it tends to be on the belt, from what I understand, and then around that pulley. If it's an over-tension belt, then you're stressing the bearing, and you're actually going to see, I think, more of a stress on that bearing aspect. Gary, I don't know if you have anything to add on that, or
I really don't. No.
Okay. Let's see. They're kind of flying in here now. In the example for a light bulb in the box, the emissivity didn't change between looking at the outside of the box versus the light bulb in the inside. Should the emissivity be adjusted based on the material being inspected?
The short answer to that question is absolutely yes. If you're measuring temperature, or what we would call quantitative thermography, emissivity always needs to be set properly. In the purposes of that example, we were just doing what we call parent temperature comparisons. So apparent temperature is how something appears to be without adjusting or considering things like emissivity or reflectivity or any of the other, what we say are object parameters. So strictly for comparative purposes, I don't remember if we left it at 1 or 0.9. But what we were really seeing there was really the comparative difference between what the temperature might be on the outside of the box versus the temperature inside the box. And so let's just say, hypothetically, we had corrected for emissivity. We used an emissivity for the painted metal on the outside, which would honestly be very, very close to 0.9. And then let's say we had adjusted for the glass light bulb on the inside, which might be 75, 80%, let's say. That temperature difference that you saw would still be that significant. And that's what the purpose of that exercise is not to get an exact accurate temperature reading, but to show you how dramatically different that temperature difference is in a matter of just a few inches of a metal box and an air gap. That the temperature difference can be significant. And I'm not talking about dozens, I'm talking about potentially hundreds of degrees difference. And that's what the thermographer needs to understand. Maybe anything to add? Or
I have nothing to add on that. You already mentioned what I was going to add. So.
All right. Here comes another one. Is it recommended to carry out IR surveys even if the switchboard is new or in new installation?
Commissioning? Absolutely.
Commissioning, absolutely, yes. I mean, people aren't perfect, and there are mistakes made with new equipment setups, and so yes, sometimes the wiring isn't quite right, or sometimes they haven't crimped or tightened everything properly. So absolutely, commissioning is definitely a very useful thing to do.
And don't forget load. It's got to be under load.
Yes, of course, it has to be under load. Yeah.
And that can be a problem sometimes. I did a couple commissioning projects many years ago for a department store. Brand new construction, and the issue was there's just no load because there were no shoppers. They were still actually painting the walls, and so not having that load can make that challenging.
Yeah, I remember one such issue way back when I started thermography. We found this very, very hot bolted bus bar connection, and it turned out when we looked at it, all the load was being carried by the bolts because the electrician had failed to remove the paper between the bus bars.
Wow.
Yeah, that was about a 400C problem.
Yikes. All right. Is soft foot or misalignment on a motor detectable with infrared?
Oh, yeah. You typically see that first with a vibration analysis, from what I understand.
Vibration would be the better tool there, but I mean, I suppose if it were severe enough and you got enough rubbing and friction involved, you'd see something with infrared, but I think you'd probably find it first with vibration.
Yeah, so you probably don't want to wait for the infrared to kick in to
find that problem. If you've seen with infrared, right? Typically in that situation, Maureen, it's been going for a while. You know what I mean? The vibration typically is something that's going to catch it earlier on in that failure curve.
All right. Let's see. In a process flow, let me start that over again. All right. Yeah. In a process flow where the reel of plastic film is moving continuously, will the infrared camera be able to give the right temp since the reel is moving and the reflectivity could be bad?
I'll give that to Gary.
Yes and no. For looking at a plastic film, plastic films, especially thin plastic films like we're probably talking about here, are very transparent to infrared. So instead of looking at the film, you're kind of looking through the film at what's on the other side. So what you need to do is you need to go with what we call a mid-wave camera with a special plastics filter that is centered at 3.43 micrometers, which happens to be a point of a carbon-hydrogen bond, and that's typical with plastics. With that filter and that wavelength camera, then the plastic becomes opaque and not transparent, so you can actually make a good measurement of that plastic. So once that's done, no problem. Then you can measure the plastic very easily.
All right. So I'm just trying to, some of these are more specific to your instruments and things that I think are probably better for you guys to handle offline. So let me just scroll here because there's a couple more I wanted to get to. Hold on real quick here. Do you have any recommendations for the frequency for thermal surveys? Sorry, frequency for a thermal survey for motor PMs.
Yeah.
That really depends so much on a facility and how they maintain and what their standards are. PMs at Intel are much more rigorous and often used than PMs in some other industries, just because Intel is so picky about it, and if a machine goes down, millions of dollars are at stake. But generally, we used to use, at least when I was doing this actively, we used to use about once a year for many industries. Some industries might go as little as every 6 months.
All right. So I think we did pretty good. I kind of hammered you guys there with quite a few questions, and there's still some more, but I think some of these are probably more a good conversation for you guys to have offline with some of these folks, so you can really kind of get into the nitty gritty, if you will. So I'm gonna just take the screen back here real quick and get here through just a couple closing slides. But again, thank you guys so much for presenting all that great information and answering all those questions. And like I said, to those of you that had some questions that we didn't get to, I promise we'll get those over to Matt and Gary, and they can either get back with you or get you in touch with the right person to get your questions answered. But appreciate everybody being so interactive and taking the time out today. Just some closing information, as Gary was saying at the end, really all of these predictive technologies, it really doesn't matter if folks don't have the training and the understanding to actually use the equipment properly. So training is certainly one of the things that we take pride in and try to provide as much as we can, just like with these webinars. So just want to point out we've got a couple online courses that we've rolled out in the last year. So for those of you that are interested in mechanical inspections and lubrication, some folks had some questions about those and how you can integrate ultrasound into that. We've got an online class for that and our compressed air survey online course as well. So just nice classes that you can take kind of at your leisure when it's convenient for you and where it's convenient, since they're online. And just like they mentioned, we'd love for you guys to get connected with us online as well. We've got our LinkedIn groups. We're on Twitter. Just a great place to share information, like Matt was mentioning with the find that they just had here at that class. That's the kind of stuff that we love folks, sharing in our community as well. Different things that they're finding with ultrasound, questions they have, ways that they're where they're using infrared and ultrasound together. We've had presentations on that, and we've got lots of customers that are using both. So it's cool to see how those real life stories. So definitely feel free to join us in those conversations and see what your peers are up to and how you can learn from them. And we also want to invite everybody to come down to our conferences that we've got coming up, Ultrasound World and Reliable Asset World. It's more than just about ultrasound. We've got presentations on pretty much all the different predictive technologies, more higher level reliability issues, the business case for it, all those good things. So it's a great event, and we'd love for you guys to join us. I'll send some information out about that as well. And finally, I'll leave our contact info up here. As I said, we did record this, so we'll get that up on our website as quickly as we can and get the recording over to Matt and Gary as well. So definitely reach out if you'd like a link to view this recording later on this afternoon, and we'll get that for you. But with that, we'll let everybody go. Enjoy the rest of their day. Matt and Gary, thank you guys so much again. Really
Thank you, Maureen. Appreciate it.
Thank you.
Awesome.
It was our pleasure.
All right, everybody, have a great afternoon, and we'll see you back here for another webinar next month.